We have two speakers today. One of our rising stars is joining us as our first speaker, Dr. Brenton Hordacre. He is doing groundbreaking work, which is optimising stroke recovery, and we'll hear quite a lot about that. Our second speaker is one of the world's leading pain scientists, and if Brenton is a rising star, I'd have to say Lorimer is probably a galaxy, but there we go. We'll see how we go with that analogy. He is not only a world-leading pain scientist, but an outstanding science communicator and educator, and I know you'll understand this when you hear him speak. Some time ago now, he did do a TEDx presentation in Adelaide, and if you're interested, you can Google that. In fact, if you Google Lorimer's name, you spend quite a bit of time enjoying what it offers you. It's quite remarkable, his reach into the media, quite remarkable. Both of our speakers are based in the impact in research concentration, impact in health research concentration at the university. Lorimer was the instigator and led that large research consortium for a number of years, in fact just stepped aside this year. And Brenton is a co-director now of the impact in health research concentration. Impact, IPACT, stands for Innovation, Implementation and Clinical Translation in health, and it not only has research into real-world problems such as persistent pain and stroke recovery, we'll hear about today, but also solving problems such as persistent breathlessness, child health and rural health inequity, and making sure that what is found is quickly translated into practice or into communication with relevant people. Let me just introduce in more detail our first speaker, Dr. Brenton Hordacre. You'll have in your speaker notes quite a few details, and without traversing each of those points, I would like just to perhaps highlight one or two of those points in particular. He's a holder of an NH and MRC fellowship which enabled him to research new technologies to help people recover from stroke. And I think one of the most important things that came out of that during his postdoctoral work in stroke recovery at the University of Adelaide was the first evidence of a time-limited period of enhanced neuroplasticity in persons suffering from a stroke. And this has had important implications for prognosis and also for stroke recovery. Brenton is internationally recognised for his research expertise in his field. He's been awarded the Young Tall Poppy of the Year Award, a Young Tall Poppy of Science Year Award, which is a really outstanding award. The Australasian Brain Stimulation Society Early Career Researcher Prize, and of course to the Brain Foundation Elizabeth Penfold Simpson Prize for the Best Neuroscience Paper. And he's had early career researcher prizes in the university as well. Please join me in welcoming Dr. Brenton Hordacre to speak to us.
Thanks, everyone, and I will need that, won't I? Thanks for coming along. Good to see you all here, and thank you for the very kind introduction as well. So my name is Brenton. If I flick through, yes. I thought rather than rising star in galaxy, we could have gone with a joke of brain and body. So Lorimer's the body, he would be up a bit later. I'm obviously going to talk a bit more about the brain side of things with neuroplasticity. So we'll get into it. I just want to acknowledge before we start that, I love my job is the first thing I want to say. And I have the pleasure of working with people. I'm a physiotherapist, so I became a clinician because I care for people. I want to help them get better. And I had a great opportunity to work in neurorehabilitation, which I love. And I worked at Flinders Hospital, or the REPAP before it closed. And just enjoyed the process of helping people get back to everyday activities after various injuries, stroke, brain injury, spinal cord injury, etc. So my job's actually very rewarding. I get to do some really cool stuff, which you'll see today, but I actually enjoy getting to meet the people. One of the cool things I wanted to show you, it's really got, I'm not going to talk much about it in terms of the scientific content, is this video. So it was awarded the best research images video a couple of years ago, I can't remember when. Great image of some of the work that we do in stroke recovery here. The scan was actually taken over the road. So this is technology that we have available in South Australia. It's research that we do here, and we look at brain pathways and connections. So all those fibres, I'll play it again if you like. So all those fibres that you see are actually pathways in the brain and connections between critical areas. And the different colours mean different things. So the bluey purpley colour is up and down, the red colour is horizontal if you want to think of it that way, and green is oblique. They're not that colour inside the brain, they're probably more of a white colour. But we like to colour them just for fun. And it looks fantastic, and we get to show people who generously donate their time into our research projects. So I am going to talk a little bit about the brain. And when I wrote this, I actually didn't think of the other meaning of the word plastic. So I'm not talking that our brains are some sort of organic polymer or inorganic polymer. I'm actually talking about the plastic meaning that it's mouldable, it's changeable. So our brains, for a long time, were thought to be this structure that was pretty standard in terms of its shape and its format and what it could do. But the more we've learnt about the brain, and probably a reason why I enjoy working with the brain, is we know that it can change. I think a great representation of that is the London cab drivers. Have you heard about the London cab drivers? Yep, some nods. Yep, not that they're crazy or that they drive very fast or... Sorry? They do, yeah. So incredible knowledge, and that's exactly the point. So I remember going to the UK to spend some time at Oxford for a few weeks, funded by the university, and we jumped in the cab and I gave them some weird group of numbers which didn't make sense to me, but the cab driver took us exactly to the Airbnb in central London. And I don't know how, but he seemed to know exactly where he was going, okay? So you would think that a cab driver in London with lots of experience is going to have this amazing representation, or map, really. What did we used to call maps? Was it Melways, or what was... what was the Adelaide one? UBC? UBD. Yeah, Melways was Melbourne, wasn't it? Sorry. So it's almost like they have this inbuilt UBD, or Melways if you're from Victoria. Yeah. Within their mind, and they could just take you straight there. So there wasn't Google Maps or anything like that helping us. So what do their brains look like? So that'd be interesting. I'm going to bring this here. I felt like when I was holding the controller, I was waving a pointer around. Was that really distracting? I don't know. I'm just going to go with the keyboard. I'm going old school. So inside the brain, there's this bit, the coloured bit. It's deep inside the brain called the hippocampus. So it's got spatial representations. Okay? So a cab driver, lots of experience, had an enlarged spatial representation. So it's called the hippocampus. Kind of makes sense. If they've had to practice lots, that area of the brain changes in the way that it's shaped or that it's formed, okay? And it also correlated with how long they've been a cab driver. So a novice cab driver, just a couple of years' experience, not a whole lot of changes there, but a 20-year, a long-term cab driver, bigger changes happening in the brain. So it could be that it's to do with the spatial representations, or maybe it's just to do with some sort of response to driving a vehicle. Or maybe it's something else, maybe it's getting older as well. But what if you swap out the cab driver and then look at the bus driver? So what's the difference with a bus driver? Set route. I don't know where that came from, but over that way. There you go, well done. So they have a set route. So the bus driver doesn't have to think, I need to get from A to B, what's the best way to get there and what are my alternatives today because there's roadworks, or I know that there's a toll if I go this way. But the bus driver just goes A to B. Okay, and when they scanned the brains of the bus driver, the hippocampus wasn't enlarged. Even when they matched it for age, years of driving on the road, or experience as well, it didn't seem to be correlated in the same way that it was with the cab driver. I like this example because it kind of tells us that what you practice can have an influence on the shape or the formation or the structure of your brain. So brains can change in response to what we do to it. For me, going back to my interest, it's clearly relevant for stroke recovery. So stroke is some sort of damage to the brain, which I've got some scans and you'll see soon. As a therapist, we do lots and lots of practice, hopefully, so that that person will get better. So it's the equivalent of being a cab driver, training to be a cab driver, practicing driving, remembering those routes. We get people to do lots and lots of movements over and over again so that their brains will change and that they'll learn to move better and more efficiently. We've got lots of different ways that we can measure that. So here's some evidence that the brain can change. This is one of our studies from pre-COVID. Everything's timeline to COVID, isn't it? So this was pre-COVID, and probably about 2017, I think. And this is what's called a functional MRI scan at rest. So the areas that are predominantly lit up in that orangey yellow colour are the motor parts of our brain. So if we're practicing stroke recovery, so movements after having a stroke, we should see some changes that happen in these motor networks. So these people aren't moving at the time of the scan. They're just in the scan trying to stay awake, which is incredibly hard, believe it or not. I've been in there once before. Despite all the noise, it's very easy to go to sleep. And this is before doing a couple of weeks of training with some special techniques that we had. And then this is a couple of weeks after. So you can see the difference. If I flick back for you, there's all these different little bits of the brain lighting up, and that motor area is not quite as big. But then it seemed to change quite dramatically. We haven't changed any of the settings or the parameters or the thresholds, really, for activation. Okay, so there's some clear evidence that the brain changes. Something else I wanted to point out here is that the brain can change, and it can be for good or for bad as well. So the brain, if we go back to the brain being plastic, we can get brain changes that are actually detrimental to our performance or behaviour. So we need to be able to measure behaviour to know whether, or some sort of movement, to know whether the changes we see in a scanner actually mean anything. So we do a bit of both in terms of movement outcome measures and also imaging or neuroscience outcome measures as well. A couple of other ways we look at it. So this is an MRI scan of someone that's had a stroke, and you'll see on what is the left side of the image, it's actually the right side of the head, just to keep everyone on their toes. Some damage to what's part of the cortex, part of the brain. Okay, so you can see a nice outline of the skull, and there should be a bit of brain tissue on that top left-hand side, and it's not there. We can look at how excitable the brain tissue is. So clearly, if there's less tissue and neurons available, and we stimulate it to get a response, we don't get as much of a response on that side. So we can measure how excitable, how easy it is to activate those pathways. You can also look at, very similar to the video at the start, so how strong are the networks or how strong are the connections between different brain areas? So we've got all these tools available to us so we can understand how the brain changes. But if brain changes are important for recovery, and if we're thinking of recovery as in good behavioural recovery from stroke, so in other words, people are going to get better, they're not getting worse from stroke, what actually happens in the brain? So we know that brain changes are important, but what if there was a time where the brain changed more? So it could change more quickly. Do you think that would be important? And of course it would be, because maybe recovery would become a bit more faster at those times. So there's some interesting data that came from mice, where all good science starts. Is that right? I don't know. We'll start with a mouse. So when they gave a mouse a stroke, and the way that they rehabilitate a mouse and give them the chance to practice to get better is they put them in an environment where there's lots of opportunity to practice. Okay, we can't really tell the mouse, I need you to do 10 push-ups today or anything like that. We just let them go for it inside the play area there. So what if we change the times after the stroke when we put them in the enriched environment? So in other words, if we give a mouse a stroke, this isn't my research, by the way, if we give a mouse a stroke, and then straight away we put them into this enriched environment for 2 weeks, how well do they recover? Well, what happens if you actually delay that by 2 weeks and then give them still 2 weeks of practice in there, but you actually just delay from the time of the stroke to starting play, really, in that enriched environment, and then even out to 35 days was the third option. And what they discovered was that the mice that got in there as soon as possible made the best recovery, and it's quite a substantial difference. So based on that, the amount of practice that they did was the same. It's purely the timing of when it started after the stroke. Okay, the good thing about mice, if there is a good thing about mice, is that you can actually give them an identical stroke, or near identical. So they can almost be very similar. So we also know it's not really to do with the type of stroke that they had. So what they did discover when they looked into this is there seemed to be some sort of genes and proteins that were increasing very early after stroke, and that made the brain more able to learn, more able to change quite quickly after stroke. So timing was critical. When we look at human data, there's a little bit of evidence to suggest this is also true. So what you see along this, I might need the pointer this time. Here we go. Let's give this a go. Or have I put it to sleep? Oh, here we go. So the line going up that way, this is a very weird sensation right now. The line going up that way is the neurological score, so a recovery. So the higher that goes, up to 100%, the more recovery someone's getting. Along the bottom axis here, you see time, and we've got some critical time points of 0 when the stroke happens, 3 and 6 months. And you can kind of see, based on the shape of that line going up this way, most of your recovery is happening pretty early, isn't it? Much like the mouse model. So the quicker you get people into the enriched environment for the mouse, the quicker they'd recover. Doesn't quite tell us the same thing. So there's a few other things happening here around brain swelling that happens very early after stroke, the environment that someone's in. But it gives us an indication that certainly most of your recovery happens quite early. This data is also pretty interesting. So we can't, unfortunately, delay rehabilitation like we do with the mouse. We try and help people as best as we can. What if you gave people extra rehabilitation on top of the normal at different times? So in the dark blue bars, they've done it in the very early, within days of stroke, an extra 20 hours a week. Sorry, an extra 20 hours total therapy. But in the next two bars, so it's subacute, which is that sort of, let me have a go over this again. This one here, so this subacute one, which is the highest one. So around 2 to 3 months after stroke, they've given them the extra 20 hours at that point. Going into chronic is when, so sort of 6 to 12 months after stroke is when they're given the extra 20 hours, and then control, so no difference. We didn't give them any extra therapy at all. And what they found there, it really did matter when you give people extra therapy. So it mattered that it was in the subacute phase, which coincidentally is actually when most people get to rehabilitation at the moment. So doing extra therapy at any time is probably helpful, but doing it at a particular time in that subacute phase seemed to be the most helpful. We didn't really have any physiological evidence, though, to test that. So a lot of my postdoctoral work at the University of Adelaide, I hope that's okay to say that word around here, just kidding, was actually looking at whether there is some evidence to say that the brain is better able to learn and more able to change much earlier after stroke. So how did we do that? I'll give you the really simple version. We brought people in and we perturbed their brain and measured some responses at their hand. Okay, and we did this repeatedly over a number of time points. So 1 week after stroke, 2 weeks after stroke, 3 weeks after stroke, 4 weeks after stroke. We kept going, okay, and those timelines spaced out a little bit, so 2 months, 3 months, 6 months after stroke, with the hypothesis that we would see the most changes that happen very early after stroke. A lot of the data was collected here in Adelaide, but there was also a portion of data collected over in the UK. So this was a multi-site study of something like 350 experiments over 4 years just to measure what's happening in the brain at different times after stroke. And the really simple summary after 4 years of work is this figure, that higher is better. In other words, we get more brain changes much earlier after stroke, and within that time frame of 0 to 14 days. So those first two experiments, 1 to 2 weeks after stroke, were really critical. People's brains changed the most at that time point. Okay? From a physiological point of view, important information because we need to get people into rehabilitation as early as possible. So what did that really mean? So if we think of someone who's had a stroke, so this is just a schematic diagram showing you that. We've got some sort of measure, let's say, of arm movement. Okay, so clearly at the time of the stroke, your arm's less able to move if it's affecting your arm. But we know, generally speaking, with what current systems are in place, most people would make about 70% recovery, and most of that recovery is quite early. So that's what that figure's showing you at the moment. What we think's underpinning at least some of that change is this upregulation or increase in neuroplasticity. So we always have the capacity for neuroplasticity in the brain, but something happens after stroke where it's this big increase, certainly within the first 2 weeks after stroke, so that people are much more able to recover much quicker. What we also know from that data, though, is that if you don't do therapy, so if you're in an environment where there's no rehabilitation offered, your recovery is less. So it's obviously important to us that, yes, the brain's more able to learn, but you've got to give it something to learn. Okay, so that what you train the brain to do is critical. You can get bad brain changes, and I mentioned that earlier, whereas if we actually had a therapist that had no idea what they were doing, which would not be a UniSA graduate, I shouldn't make university jokes, should I? And they were training the wrong thing, then that's what the person would learn. Okay? So we need to make sure that the therapy provided is good quality therapy, that that person will get better at the movements that they're wanting to do, because the brain's ready to learn. So this time point here is really critical. Okay? And in fact, that information that we've generated has helped change clinical guidelines. So there is guidelines now from Australia, but also UK, US and Canada, all recommending that rehabilitation starts early after stroke, as early as possible. It's also led to changes in clinical practice. So in the US, there's some data that's been published now at the Johns Hopkins Centre for Stroke Recovery, and they've reconfigured their acute stroke unit so that rehabilitation happens straight away. As soon as someone's medically stable, they get them moving so that they can recover as much as possible. I think these are fantastic outcomes. I think there's some really interesting questions that we can still explore in this very early stage after stroke. But I kind of got interested in the other end of the scale. So I mentioned very briefly that we kind of know most people recover about 70% of their recovery. So it's rarely a complete recovery. And if you know of anyone that has a stroke, or has had a stroke, I should say, you'll probably be aware of some sort of deficit, whether that's speech, sensation, cognition, movement-based things. And I suppose it got me thinking, what can we do at that other end of the scale so that people can actually get a bit more recovery? So if I think of the neuroplasticity things, we've certainly got some evidence to say that if the brain can change faster, we get more recovery. We certainly know that the brain can always change, because it doesn't matter if you're an old London cab driver, or if you're someone that's had a stroke, or if you're like my children learning to skateboard at the moment, which is a bit scary. The brain's always got this capacity to change. But what if you could just stimulate it a little bit more, so it could change a bit faster? Could we get a bit more recovery for those people that haven't fully recovered from their stroke at this time? So I'm going to talk a little bit now at that really chronic end, I suppose, of stroke and what we've been doing. I mentioned before I love working with people, so I love hearing their stories. And this is what people tell me who are anywhere from sort of 6 months onwards after stroke, and I'm talking into 20 years after stroke. This is actually my, probably can't say, a very close friend of mine who became a friend because of research and coming into our studies. And he told me, after walking into our clinic, I should say, that the doctor told him he'd never walk again, that he'd be in a wheelchair for the rest of his life. And we hear this a lot, where the doctor will say things, or a doctor or a neurologist will say things such as, this is as good as you'll be. Beyond 3 months, there's no more recovery. So in other words, you're going to have a plateau at 3 months with your recovery, and just get used to living like that. Get used to the impairments, change your lifestyle, change your work if that's of the age that you are, so that you can live as best you can. We still hear that story today, even with patients that are just months after stroke. That message is still out there. This is extracted from a publication in a leading neurology journal that was published in 2022, so very recent. And the statements from the neurologists that wrote it were most improvement in the first weeks, which is true. I've shown you the data. Okay. There's a plateau at 3 months. Look, I think that's true. And again, we saw that with the amount of recovery. And at 6 months, there's a stable chronic deficit. So in other words, what you are, this is what they're saying, at 6 months you'll be for the rest of your life. So if I'm thinking of looking at chronic stroke, probably the first thing I'm thinking is, are people actually even going to recover? So we might increase their neuroplasticity. Are we even able to get them to recover more? When I talk to the clinicians, the thing that comes through from private practices in the community are statements like, does my 1 hour of therapy or 45 minutes of therapy actually make any difference? So the average duration of stroke rehabilitation, if you're in the chronic phase, so 6 months onwards after stroke, probably about 45 minutes a week of practice. If you ever learnt to play the piano or play an instrument, learn to skate the skateboard or whatever you want to do, probably doing more practice is better, is the first thing I'd say. And if you're to do 45 minutes practice a week, or half an hour in some cases, it might not actually be enough to actually get much change. So when the neurologist says this is as good as you'll be, maybe that's a reflection of we're not giving people enough chance to practice, to get better, even though they're months or years after their stroke. So we started to explore the question of whether is it about how much practice people are doing. And if you know a little bit about brain changes and neuroplasticity, you'll know that dose, or the amount of practice, and the intensity of practice are really critical to drive brain changes. So about 2 years ago, we established something called an upper limb boot camp, where people came in 3 hours. This is chronic stroke survivors from the community here in Adelaide, 3 hours a day, 5 days a week for 5 weeks. So a short 5-week burst of intense practice. There was a bit of homework in there, and if you do the maths with the homework on top, it comes to about 90 hours of practice. Okay? If you go back to what people normally do, somewhere between 45 minutes-ish per week for 52 weeks, so even in a year they wouldn't get this amount of practice. And we're doing it in 5 weeks. We did it in a group environment. I did that from a pragmatic point of view of more data coming through, because otherwise if it was one person every 5 weeks, it'd be a very slow study. And we had 1 physio and 4 patients. And the fascinating thing about the group thing is it's actually probably been the best bit about the study. With the support network that the group of 4 patients has generated, there's tears at the end of 5 weeks, and they stay in contact. And it's been an amazing experience. And we get OT, physio students as well coming in. All the clinicians always ask me what is in boot camp. So what are we actually doing? I don't think we're doing anything special. Okay, we have some really good clinicians. We're bringing up the idea that if the more practice you do, the better you get. So that might be something special in terms of the amount of practice. We have some interesting toys, which I'll play the video for you. That's our tallest stroke survivor ever, and me, because I'm not that short. And this is a robotic device. But it's just another tool. We don't do this for the whole 3 hours he's there. We do lots of different things. Okay, and we have some different options. There's actually nothing special. And in fact, you can see just basic cones that are being stacked. Okay. We keep people busy for the whole 3 hours. It's exhausting. If you know anything about stroke, fatigue is an issue. The fascinating thing about this study, I thought I'd be begging people to come every day, as in fatigue is an issue or transport's an issue. But the truth of it is I can't get them to leave after 5 weeks. And it's so dramatic that we actually created something called Reboot, which is an add-on program, because people are so good after 5 weeks, they actually get their own equipment out and they put it away at the end of the session. And they still need the physio there, but we certainly don't need as much input. So Reboot is actually a 1-to-10 ratio. Okay? So we are more than happy for people to keep coming back, and it's been a shock to me how little begging I've had to do, and how little enforcing of no, you can't come back, you can go to Reboot, just for the study's sake at this stage. So what does the data say? Because I've told you some really great outcomes. So the change here, the fugal mire change on the y-axis is an upper limb measure. The higher you go, the better. So clearly we've got a pre and a post measure. So just doing your regular activities, you get about a 0.5 point improvement in terms of upper limb movement. So that's probably people just doing an hour a week or doing whatever they want to do in their own home. When you come to boot camp and you get your pre and post measures after the 5 weeks, it's about a 12-point improvement. I actually don't think there's anything that matches that. As in all the new technologies, all the drugs, I'm not aware of anything. The closest that it comes to is things like constraint-induced therapy, if you've heard of that, and that's about a 5-point improvement. Virtual reality amazingly had about a 4.5-point improvement. But there's nothing that's into double digits. So what does it mean, though? That's a number. So what does that actually mean for someone? Well, we know with these scales we have something called what's a meaningful change for the patient. So what should someone actually perceive? And anything above 5.25 points is meaningful to the patient. We're more than double that at 11.5, I think. So they should definitely perceive changes. What have they told me? This is actually the really tall gentleman who wrote this. So his stroke-affected hand was the right hand. He was a farmer for many years. And what he was trying to draw there was his farmhouse in the house picture. It's the first time he's been able to write or draw with his stroke-affected hand. Okay? He actually could write, rehab is hard, and I enjoyed keeping that because I thought, yeah, it should be hard. And good on you for writing it and being honest, because it is hard. And I warn people about that before they come to this study. But he's actually able to write legibly and being able to, that somebody else can read it. We've had other people come through. In fact, another great example is someone who said that they could eat popcorn for the first time. So popcorn is not my favourite food because I used to work at Greater Union at the cinema and it smelt all the time of popcorn. But his important thing for him was a family thing. On a Friday night, they'd sit down and watch a movie as a family. And he loved popcorn and he wanted to be able to eat popcorn. He could do it, but he had to use his other non-affected arm. Okay? But for the first time, he could pick up popcorn and eat it. So he could actually grasp something, bring it to his mouth and release. Big change in 5 weeks. We've had people who have got their driver's licence back after the 5 weeks. There's a bit of a process, but they've got so good with their upper limb use that they could go for their driving test again. What if we could do better? That's pretty good, 12-point improvement. I said there's nothing better out there, but I don't know, inside of me I was thinking, what if we could just do a little bit better? Or what if we could refine the way that we do the practice again? So 5 weeks, really intense, but what if it doesn't matter what you do inside the 5 weeks? So what if we could increase the neuroplasticity again somehow? So they can do it in mice. So in this mouse example, this study here, what they did is gave a mouse a stroke, but instead of letting the mouse into that sort of enriched environment again, they kept the mouse separate, so it couldn't do any practice. That's a bit mean, isn't it? So it couldn't get any better because it doesn't get the chance to practice. So like I said, there's an increase in neuroplasticity after stroke, so the brain's more able to learn, but they didn't let the mouse learn. So the mouse didn't get any better. Okay, so it does matter what we do still. So there's still a job for physios. But then after 35 days, they gave the mouse another stroke in a different part of the brain. Okay, this was I think it was a visual area from memory. And then they gave the mouse lots of practice straight after. So totally unrelated to movement, but after the second stroke, they let the mouse practice lots of movement. It got better really quickly. So what they're saying has happened is that the second stroke has actually reopened this period where the brain's really able to learn again. We can't do that in humans. But it gives us a clue that maybe you can manipulate the brain's ability to learn in some capacity. So another arm of my work has actually been trying to figure out ways that we can do that, and ways that are reasonably easy to do and safe to do for a regular trained physio. So that if we could discover that, we can tell them about it and then they can start doing it in their practice. Because we want our work to be taken up and implemented straight away by different people. So here's a couple of things we've tried. We've tried this, this was pre-COVID as well, this home brain stimulation device. And I say that because it was pre-COVID because it's actually Skype. People don't talk about Skype anymore. It's all Zoom for some reason. So we used Skype and saw them at home. They pop something on their head, turn it on, and they do heaps of practice with their arm, just like the images are showing there. So we gave them a kit. They could practice some hand tasks or turning coins over. It was tailored to their level and ability, but they did an hour a day of practice. And these are people that are years after their stroke again. An hour a day is not much, but it's a little bit more than normal. Okay? Some people got the real brain stimulation. Some people got a placebo one, so it felt like the real one, but it wasn't actually doing anything. And this is what happens. So we have, again, our same sort of measure, so higher is better in terms of the measures going up. And if you have a look along the, let's see if we can get this thing back. Here we go. It always takes a second. Along the baseline, along the bottom line here. So we've got different time points. So baseline is before we started the study. This is then after the brain stimulation. And then we actually followed them for a little bit longer. So even though they're finished with us really, they just come back in a month later just to see how they're going, and then 3 months. So if you got the sham stimulation, just doing an hour a day for 2 weeks, so 14 hours of therapy, didn't really do a whole lot, about 1 point on that scale. Okay, keep in mind I said about 5 points is really that critical measure. But when we gave them the real stimulation, they had a much more dramatic improvement. In fact, they just got to that 5-point mark after doing 2 weeks of treatment. So we're certainly seeing a boost or an increase in what they were able to do in terms of recovery. I always think the fascinating thing on this figure is that they actually continue to get better. So we didn't do anything at 1 month, after the treatment in 1 month, or right out to 3 months. But for some reason, people got better. And the only thing I can think of is that they actually had the ability to do more with their hand, and then they kept doing more with their hand. So if you could start to brush your teeth with your affected hand, you kept using that hand to keep brushing your teeth. Or you could open a door handle or turn on a light, you keep using it. So maybe it's some sort of spontaneous engagement in rehabilitation that happened there. We don't really know what that is, but it's sort of a fascinating outcome. The clear thing from that is that we could clearly stimulate a brain, and it does seem that people will get a bit better. We also tried this virtual reality task that we invented. I got a poor little honour student to do this because I had no idea if it would work. And she invested 2 years of her life into the study, and we created this content where you didn't do anything with your hands in virtual reality. You just wore the goggles, and it was like you're in this, it's like the virtual world in a virtual reality. And you saw all these tasks, and there was a story behind it about getting ready for the day, and you're actually doing a juggling show, so you practice some movements, and you did some hand warm-ups, and you packed your bags. A lot of hand movement-based things. And this is very early for us with this one, so it was just healthy adults we were testing it on, and we just measured some brain changes. The interesting thing with this is we did see that when people had the real treatments, we also gave them a sham one where they just watched a movie for a little bit. When they were watching this and they really thought about the movements, just like an action observation or a motor imagery task, and they really thought about it, it seemed to change brain activity. So again, it's almost like we're priming the brain. So that then if we followed it up with a bit of physiotherapy, they might start to learn a bit better with that as well. So that's something that we're exploring. I'm almost finished, so I can probably do your question at the end if you like. Yep. Okay. Will be a test. So we're working with University of British Columbia. So we just had a visiting research professor come across, and I'm heading over there May. I haven't booked my flights yet. To just continue this line of thought around how we can use virtual reality and some action observation, motor imagery stuff just to prime the brain activity. You don't actually have to move your hands, so it's kind of perfect for someone that might have been affected by stroke. This one's also some student work that was just published actually. And what we did is get people to exercise on a bike. So who would have thought exercise is good for the brain? It's certainly good for cardiovascular system, but it seems beneficial for brain health as well. And what we found here is that just 20 minutes, moderate intensity. So we didn't even make them go that hard, 60 to 80% of your maximum heart rate. So it's not even a hard workout. 20 minutes, continuous cycling, improved a neuroplasticity measure that we have for the hand. So the hand didn't even do anything when they was riding the bike. For some reason, we're getting an increase in brain activity and a priming of the brain. So maybe, there's actually quite a lot of evidence for cycling in brain health. Maybe we're thinking that we can use cycling or some sort of exercise to prime the brain so that therapy will be better and people get even bigger improvements. And last one of these, I've got a student who is working very hard to stimulate the vagal nerve. Who would have thought having your ears stimulated could be a good thing? So there's a little branch of the vagus nerve that actually innervates the inside of the ear. I feel like I need to wash my hands after touching my ear. So the vagal nerve, there's actually a big branch that comes down through the neck. There's been a lot of work where they do surgical implants of stimulation of the vagal nerve. So not quite as easy as, say, just putting a little earpiece in your ear. So we're going to try this one where we pop something in your ear just to see if we stimulate the vagal nerve, what happens at the brain. When they've done it in animal models, and certainly some early human evidence is, that you seem to get this change in the neurochemistry in the brain, so it promotes learning. And the good thing, I think, for us is that it's not specific to a region. So it's not like we're just getting it in the frontal part of the brain or the motor cortex. It seems actually quite uniform across the whole brain. So he's in the middle of a study at the moment, trying it for walking and balance recovery after stroke. But he did do some work very early on looking at healthy adults and just seeing what the brain changes are. So what we're seeing here, I'll grab my little pointer again. So we've got a measure before and after, so a pre and post of stimulating your ear. It's not a nice sensation, I must admit. But this was a sham, okay? So nothing really changed with that measure. But when he actually did the real one for 60 minutes of stimulation, you get this huge change happening in inhibition within the brain. So we're reducing the inhibition. So it actually makes the brain more excitable. And it's a measure of excitation-inhibition balance. It's a measure of, or a marker of neuroplasticity as well. So he's now on to the behavioural side. So is this brain change actually a good thing? And we'll find out soon. So I'll finish up in a second. So what's next? We've got this idea that the brain can really learn quite well after stroke, but recovery is not quite complete. So I'm kind of interested, first of all, we've got boot camp. Okay, so that really high dose of practice actually does seem to work. And it works really well, if I'm completely honest. Better than I thought. So maybe we're going to give people a little tick up there at the end, get even more recovery. What if we can just tinker with that a little bit? And I don't know, my best guess is that this is just a small change. What if we could do something to increase that neuroplasticity there? And we just get a little bit more when we do boot camp. And I don't know. When I say best guess, I'd probably guess 5 to 10% difference. Like, I don't think that's a huge difference with the neuroplasticity side. I think the practice is the critical thing, and lots of practice. So the plan for the next, probably retire in 20 years, I reckon, probably 20 years, is to actually take boot camp a little bit further. So we've been doing in Adelaide, we've been doing some great things and getting some great outcomes. So we've clearly got a clinic set up just down the road from here, actually. And we'll continue to do that, to offer a boot camp service, and we'll keep testing these things that might increase the brain's ability to learn. And where they work, we'll put them into boot camp. But there's some really key hotspots in South Australia. So we've worked with the Department of Rural Health, and make sure I haven't gone too far, yep. And they've identified for us, based on census data, where there's proportionally more people living with stroke. So the average in Australia, across like all of Australia, is about 0.9% of the population is currently living with stroke. But I can tell you in Whyalla and the surrounding regions, which is the big circle there, so Port Pirie, Port Augusta, it's about 2%. Okay, if you go to Victor Harbour, it's about 2.5%. So again, thinking an older demographic that's living probably down that way. Mount Gambier's quite high, and Port Lincoln as well. Okay. Luckily for me, the university has a very nice footprint, and we actually have some clinics that are located in these areas. So we're looking into the possibility of actually seeing if we can pick up what we're doing with boot camp and going to these hotspots, really, of where there's people living with stroke. And then when we discover things that might help the brain learn better, can we also throw them into boot camp and just see how better people can get? Thank you. And then obviously just a series of acknowledgements of many people that have helped me along the way there. Thank you.
Brenton, I think we've run out of time for questions. Am I right about that, Zoe, or do we have a little time?
A couple of questions? We can take a couple.
A couple of questions? Marvellous. Right. And then we'll go to afternoon tea. Right. Hands up and we'll get the mics to you. One at the front there.
My question was when you were saying that people were recovering after they had learnt a little bit more, and so perhaps there was the idea that you were practicing more, using it more because you now had the ability to do it.
Yeah.
How much of that could be linked into old memory of the brain remembering what they used to do with that hand, or would that have been gone with the stroke? So perhaps that old memory was actually helping them to increase their ability once they had actually got some of the ability?
It could be. I think it probably depends a little bit on characteristics of the stroke. So when you say the old memory, so in other words, how we plan a movement could still reside there, but the execution of the movement may not be possible. And
it was just like once they'd remembered they could eat popcorn with that hand and they learned how to do it, they then became more proficient at it because part of that memory might have been still there. That was just a thought.
It's possible. I think there's a lot of variables that would come into that in terms of the stroke location, how many years since the stroke, have they been trying to eat popcorn but doing it a really different way? Yeah.
And I also thought about how much practice were they having at home, whether some people were practicing more, and like you were saying, practice makes a difference.
Yeah.
And whether that was going into your study, whether those factors were...
Yeah, so, we don't actually have a measure on what they were doing after the treatment had finished. Certainly within the study, like while they were in the 2 weeks of treatment, everyone was doing the same. I can't imagine why, with a randomisation process and the size of the sample, it was about 65 patients that were in that study. I can't imagine that I'd have to have a look, but I can't imagine that we would have people that were much more motivated in one group and not the other for rehabilitation. Yeah. Yeah. So that wasn't boot camp. This is pre-boot camp. So boot camp's 90 hours in 5 weeks. That was just 14 hours in 2 weeks. Yeah. So, yeah. Practice makes perfect, yep.
One more question. Zoe, I think over to your left.
Hi. I was wondering how this research would go with something like sight versus a limb that's become disabled. Does exercise carry out the same potential with something like sight, which is a little more passive?
I don't know with sight. I don't know with sight in humans. I know with sight in cats, believe it or not. So they have done some stuff with cats, and they actually, again, when they perturbed the brain and then they did some sight training, which was actually just looking at visual grates, they could see that the neurons, because it's an animal study, they could see the neurons were reorganising much more efficiently. What I was going to say in humans, for speech, there's some good evidence coming out that's mimicking what we see with movement, so that there is this critical time after stroke for speech recovery, that the amount of practice you do for speech training influences how well someone will learn to talk again after a stroke, and that there might be things that they can do there as well to increase that efficiency of learning. So I don't know with vision in humans is the only thing I would say. I would imagine that it's probably similar.
So that would be eye exercise.
Yeah, it's
Vision sort of passive, isn't it?
yeah, because you're well.
Control.
Yeah, so I think speech in some ways might mimic what we see, where people learn to use their arm, they'll start to spontaneously use it more. Because if you can learn to say a few words, you'll start to talk more in your family or your society that you live in.
Yeah.
With speech, I think it depends a little bit on how severe the symptoms are, but if you can see, obviously you're getting visual input all the time. But I'm not aware of anyone doing that sort of work.
Have we time for another question? Or I know that anyone who doesn't get their question answered can actually come down and talk to Brenton in the break. But Zoe, you're my time person, okay. All right, and I know there's one there, but I think it's too late, alas. But please come down later.
Yeah, it's been a while ago that I was reading up on Neuralink, the
Elon Musk.
Elon Musk sort of company. Do you know anything about that company and what they do?
It was a computer chip inside the brain. It's about all I know. Is that right?
Yeah, I think so. When I saw you talking about the stimulation in the ear, I thought, that might be something that they are working on as well. I'm not sure how they stimulate the brain.
I don't know if it is a stimulation. I thought it might have been a computer chip to replace some of the processing that happens in the brain. Is that right? But there are implanted brain stimulators that do exist. And certainly in Parkinson's disease, there's good evidence that they can help. Yeah.
I think we probably need to stop at that point. I will be thanking both speakers at the end, but I'm sure there'll be a lot of questions of Brenton in the break. Welcome back. Welcome back to our second part of our Successful Ageing seminar today. I made a promise that I wouldn't talk too much about Professor Lorimer Moseley, AO, but I'll try to say a few things, so I give him lots of time to speak to you. But he is really quite a remarkable human being. As you will see from the presenter's notes, that the wording of the AO award is quite extraordinary in the sense that it finishes to humanity at large, service to humanity at large. I don't think I've ever read that in an award from the Honours Secretariat. But you have the other details, and one of the things I mentioned earlier, that Lorimer is one of the world's leading pain experts. So I thought just maybe a couple of extra metrics to help you realise that this is indeed so. He also has a Doctor of Science, as well as his PhD. He's published around 400 papers, and over his 20 years, he's attracted about $22 million in research grants. So he's a serious researcher. But the point that I really wanted to make was that he is a committed communicator, educator, and someone committed to empowering people in relation, if you like, particularly to pain and persistent pain. And some of the presenter's notes that you have illustrate that quite well. For example, the Pain Adelaide Stakeholders Consortium is about people putting their heads together to make translatable approaches to people with persistent pain. And there's something that very close to Lorimer's heart is the Pain Revolution, the grassroots non-profit initiative. And the mission there is truly worth reading about, to ensure all Australians have access to the knowledge, skills and local support to prevent and overcome persistent pain. And it has a really significant rural outreach there as well. And the other final thing to say is that another area where Lorimer is very much involved is in his research group, the Body and Mind Research Group, which investigates the role of the brain and mind in persistent pain. And if you think about it, pain is 20% of people suffer from pain, and the actual cost of dealing with that pain is, I understand, more than the cost associated with managing cancer and diabetes combined. So it's a major, major problem, pain. So finally, it gives me the greatest pleasure to welcome Professor Lorimer Moseley AO to speak to you today. Thank you.
Wow, that's so generous. Thank you, Ruth. Hello, everyone. So I've got the difficult job of keeping you all awake after your little biscuits. Just want to do a quick survey of the assortment of biscuits. Raise your hand if your favourite biscuit is the Scotch finger biscuit. Yeah, exactly my point. Oh dear, gluten-free Scotch finger biscuit. Really? Okay, thanks, Ruth. I love it when someone mentions Pain Revolution and acknowledges how close it is to my heart. I think if you want to learn about something really cool happening in the pain world, type into your web painrevolution.org. It's really cool. It's driven out of University of South Australia, but it involves people from all over the place. And I love it when someone else says how important the problem of pain is. So I'm used to reeling off statistics about chronic pain because I'm used to asking people for money. And when we ask for money, we say, you know, did you know that chronic pain is, according to Years Lived with Disability, humanity's most burdensome pain problem? Did you know that people with chronic pain retire? It's the most common reason for leaving the workforce early, and these people retire with less than 10% of the savings of the rest of us. Did you know that it's invisible and we don't really have a structure in place in our country to deliver care to people with chronic pain if they're not on a compensation claim? There is no avenue for care. Did you know that the philanthropic and government support to provide treatment for depression each year is about 160 times the amount for chronic pain? So I love it when someone else can kick off a rant like that I can follow up with, we've got to get behind these people. They're like us. We all know someone. In fact, there will be, by statistics, a bunch of you whose life is not as good as it could be because of pain most days. Anyway, let's lift the theme a little bit. So change is inevitable. I loved your talk, Brenton, and I'd like to thank you for wearing the same shirt today as you did in the Channel 10 news show because I wasn't sure it was you for a while. Okay. And while we're on clothes, I'd like to make just like a little bit of gratitude from you people for the fact that I'm wearing a shirt today, because normally I will wear a T-shirt to do talks like this. But I said to my parents, what do you think, T-shirt? And they both went, shirt. So I hope you appreciate that. And then I looked at what sort of jeans I could wear with a shirt because I don't own any pants, right? I only own jeans. And I found this pair. They were the only pair that didn't look like I'd been working in the garden. And I found this pair, and I got these in the mail about 6 years ago, and I haven't worn them before today. And they're just a little bit tight. So I'm struggling a little bit to breathe. And the third part of my attire is my shoes. Ruth, would you be able to join me up here? I wore these shoes today because they're the closest I've got to Ruth's shoes.
Lovely.
Okay, we are standing on the you guys are sitting, I'm standing on the Great Southland. These are all the nations of the Great Southland. We are obviously on Kaurna land. I pay my respects to First Nations people for their extraordinary connection to land, to sea, to the waterways, and as we're starting to realise, to the air, biological connections that we now think are in place, which are changing, potentially revolutionising our understanding of brain and body, because we really have to talk about brain and body and world, a unified existence. And that's very relevant to my talk and the way that we know things. I guess I'd love to also pay respects to the Indigenous ways of knowing things and the knowledge holders of our First Nations people, elders past, present and emerging. I also have to let you know that I sleep with the devil regularly. So these are the people who give me money so that I can do my research, or maybe I can travel to a conference, present at a conference. Some of them actually give me actual money. The ones most relevant here, there's probably none particularly relevant to this. I no longer have Port Adelaide Football Club because this is the last 5 years. I used to work for Port Adelaide Football Club. And not a word of a lie, I announced that once, and 2 people got up and left. I suspect they were Crows fans. Anyway, I'm no longer involved with Port Adelaide Football Club, most of you will be pleased to know. I have, however, worked with a couple of the Crows in the last couple of years, but not for the club. Okay, so I want you to imagine this scenario. This is Brenton in an earlier stage of life, and he was walking across the road, and you might be able to see how do I do this? Anyway, you can see the drawing pin on the ground. And I want you to imagine what happens to this man when he treads on the drawing pin. In that scenario. Ouch. What sort of behaviours will we see when he treads on the drawing pin? Like, you could watch from a distance and you'll think, that guy's trotting on a drawing pin. Because he will do something like this. Okay, cool. Okay, so we're on the same track. Why does he do that? Something that fascinates me and has driven my career is that sort of question. Why? How does that happen? Why is it that when he treads on the drawing pin that happens? However, in this situation where just before he treads on the drawing pin, a car comes around the corner at speed with loud music playing, and now something like this will happen. Wow, he'll run right over here, he'll swear at the driver, he'll say, you guys okay? Yeah, I'm okay. Oh! So why is that? Like, how does that actually work? In that instant, his brain is able to make these incredibly sophisticated computations and decide, you ought to be frightened. You need fear right now. That's the thing that's going to protect your livelihood. No car, the brain thinks your toe is in danger and needs to be protected. And the behaviours are totally different behaviours. Why is that? Well, one thing is because of the models we have. And we didn't rig our talks today. In fact, I'm not doing what I told you I would do. I'm sorry, Brenton. Because I was thinking about, my role was the plasticity, the changeability of the body. And the more I thought about that, the more I really was just reminded that you can't separate the two, the brain and body. We are a unified human. And the more I thought about the excitement of this plasticity, I really thought about the excitement of the brain's models of the body. And I'll try to get across what I mean by that. But Brenton's lovely talk talked about the taxi drivers and how they have these amazing maps of London in their head. Well, watch this. This is going to be great. Brenton doesn't know I'm going to ask him to do this. Brenton, can you stand up, please? In fact, would you be able to stand somewhere about there? Face everyone. Okay, now I'm going to hold the microphone up in the air, and I'm going to ask Brenton to close his eyes and go and get the microphone. I know he didn't know I was going to do this. I hope this is okay. I hope you're not going to fall over or something when you close your eyes. I was going to ask one of you guys, and then I thought, just imagine if you had some weird close your eyes and fall over disorder. That would be so bad for me legally. So, Brenton, tell me now if you've got one of those. There you go. Okay, so I'm going to put the microphone there. You got it? Yep. Hang on, open it, your eyes. There it is. Yep. Close your eyes. Go and go. Look at that. Look at that. Thank you, Brenton. That is fantastic. Just think about how sophisticated that really is. Like, he had to take steps. He had to map that out. Where is it? Where is it in space? Where is that microphone? And he can hold it in his head in an area in space in the world. Imagine how good a taxi driver would be at doing this. The maps of the world. But what we often forget is that Brenton is relying as much on the maps of his body. He needs to know how big his body is, what position his joints are at, what is the information coming back, what does that mean, the information coming back from his body. He would be using data like the wind on his face to make sure he's in the direction he wanted to go. His arm is coming up to reach for the microphone, and he is getting data back from his arm saying, yep, this is all going to plan. Your arm is lifting. It's the same weight as it was. All of this data is coming in all the time, and having had no warning, he's easily able to do that task. And in fact, we could start doing things which we don't have time to do, but we could say, okay, this time, Brenton, I'm going to move the microphone 3 metres to the left. And he could still come pretty close. He probably wouldn't get it, because he's not that good at stuff. On that, isn't he great at stuff? Wasn't that stroke recovery stuff just amazing? Congratulations. It's really important work that Brenton is doing for humanity at large, but also for South Australia. It's just really good stuff. So your marvellous models can do things, and the reason that your brain's able to cope with all of that computation is that the brain doesn't really look for information to know what is happening. It just looks for information to know what is not expected. Because most of what the brain receives is expected. So it's a nice little trick of efficiency. Say, okay, just tell me that which I did not expect. And I'm going to do an experiment with you guys to demonstrate sort of how that works. So here are 3 numbers. And without saying to anyone else or to me, just work out how those numbers are connected. I'm going to put a series of numbers up, and the task is, how are these numbers connected to each other? So that's the first set, 7, 14, 28. Come on. I heard it. I think it was over here. There was a whoa. So what you will, this is what, if we did this with 1,000 people, we would notice that many people think they've got it after the first one. And now's time, we're amongst friends, just not necessarily yours. But now's the time, maybe confess. After that first 3 numbers, did you think, I've got this? Who thought that? Yeah? Some of you will have been convinced by the second one there. Yeah, no, I've definitely got it. And then, come on. Some people, when the 0, 1, 2 comes up, think, oh no, I don't. But most people don't conclude they haven't got it. Most people conclude, no, I've still got it. And that's the first part of evidence to say, well, that's crazy. How many ways can you look at 0, 1, 2 and realise it's not doubling? It's not doubling, right? But most people will see that, but because everything else fits, they'll just put it out of their mind. And they think they've still got it. But when they get to the next example, not much later, they realise, oh, hang on, I don't have it. So who thinks they do have it now? How are they related? They get bigger. Brenton got that, but he's, every night he goes home and puts electrodes on his brain and... All right, I reckon we've got flat batteries in our thing here. So, these ideas were first proposed by a guy called Thomas Bayes. And some of you, does anyone know about Bayesian theory? Are there any physicists or engineers or mathematicians? Biologists? No, you don't have to explain it. Well, you can explain it with the easy form. There are entire books on Bayesian theory, but really they all come down to this example here, that because of your models of the world, so your expectations, your models produce your expectations. You have new data coming in from the body or the world, then whatever comes out the other side will just represent a mix of those two things. Correct, but I don't want to let anyone in on that just yet. But this is the easiest version of this way of thinking, and it's really nice for us in neuroscience and in pain to think about this, because pain occurs when the model of the body it suggests that it's in danger or it needs protecting. Pain doesn't actually get generated at the place that it hurts. And the way we can prove that is, if we have any volunteers for this, you could volunteer to have your leg surgically amputated and then removed, and we could keep that leg really healthy in some really weird artificial environment. You move away from your leg, but it's you that will be having leg pain. That's phantom leg pain, even though you don't have the leg. And we could put the leg in some kind of industrial food processor and mash it up totally, but that leg would not feel pain. It's you who has the pain. And that's one of the reasons that we know you have pain, because of the models in our brain of the body. And if the model of the body says this body part will not cope with the stress about to be put on it, then the brain tries to stop you from putting the stress on it. And it does that by giving you pain in that body part. Models are really important. When we learn something, and this is about bioplasticity, and this is my way of sort of sneaking into the brain via the body, when we get data that suggests that the expectation was wrong, we may decide to change the model. And ultimately, that's what we're trying to do with treatment for persisting pain. Ultimately, we want the brain's model of the body to be consistent with being resilient, to being able to cope with this mechanical load it's about to get. But we only want that if we're convinced the body is going to cope with that load. Hang in there. If this is tricky, I understand. Oh, can you play that? So there's a video coming up, but it's got sound. I'll just go to the... Oh, hang on.
I think Brexit is a really terrible idea.
Okay, so did you notice what happened for most of you? The first time you heard that noise, it was nonsense. Then you had a new model. So the first time you heard that noise, you've got no model of that noise. The sound comes in and you hear that noise, nothing in particular. Then you get data where you have a new model. The man saying, I think Brexit is a really terrible idea. You hear exactly the same noise comes into your ears, but now what you hear is a weird sounding, I think Brexit is a really terrible idea. That's clear evidence that what you hear is the response to the model and the sensory information. And I'll say that again because it's so cool when you think about all the other things we experience. Feelings, sounds, sights. When the model is changed, so you're expecting to hear something along the lines of, I think Brexit is a really terrible idea, and you have sensory data coming in that used to be meaningless, now has meaning, and you hear something different. Just a little step to the left to think about, well, instead of hearing something, I'm feeling something in my body. Then if we can change the model, the same sensory information that we were getting before may very well end up in a different feeling through this way of understanding things. Let me persevere. This is pretty hardcore, right? Mistakes are really critical for us to change our brain. So, I'm going to give you all a bit more homework. I'd like everyone to do that. Can you do that with your fingers? So that will be difficult for some of you, easy for some of you. Star Trek people will have it covered. Okay, and then just change it to that. So 2 in the middle, 1 on either side. Now this time just go back to that position again, to the 2 either side, and look at what you're doing. And you might see once you're looking at it, oh, I can change more easily when I'm looking at it. Why is that? Because your sight immediately sees the mistake you're making when you're trying to do it. And you get visual data saying, that's wrong. And you can correct it. So here's your homework. Raise your hand if you've got grandchildren. Great. Okay, the next, just practice this for a week. And then see if your grandchildren are as good at this as you are. And they will not be, and you'll get a lot of points. Okay, here it is. So with one hand, do that. So that's the 2 either side. With the other hand, do 2 in the middle. That can be difficult to do. And then practice. If you practice that for 1 minute every waking hour for the next week, you will be doing it accidentally, but you can show off to your grandkids. And when they learn to do it, don't give them the trick of looking at it, because they'll be going, oh, I can't do it. And you will be able to just say, it's quite easy. But as you learn to do it, look at it. And that's what allows you to detect mistakes. So when we're thinking about pain, and now it's not, the output is not a movement like this, it's a feeling, let's say in your knee, you have knee pain. One thing that happens with pain is that the longer you have pain, all of the things we're talking about happen. You get better at making knee pain, for example. The longer you have knee pain, the better you get at making knee pain. Just because we know this is how the system works. Now that's got a really good side in that it means your knee's being really well protected. It's got a bad side because it's probably being over-protected. And if that gets sensitive enough, the information coming from the knee may very well be saying, no problem here. But the model that you've got of your knee is that it won't cope and your system doesn't detect the error, the difference. And then we're in a challenging situation because you keep walking up the stairs, it keeps hurting, it keeps reinforcing, and we're in a bit of a vicious cycle. Our models of things are very complex. So this is 3 people, and I think by looking at these people, let's make a decision on how attractive they are. As a group, let's judge their attractiveness. Okay, I'd like you to raise your hand if you suspect that these 3 people, they're quite attractive. I think they are. They're quite they look like they'd be quite attractive, I think. Okay, so I want you to yell out at the top of your voice when you discover that your model is wrong. Well, it doesn't matter how long you look at these, you're thinking, yeah, they are beautiful. They are beautiful people right there. That's your model. Okay. Oh, they are just not very attractive, are they? They're still not very attractive. Oh, hang on. Yeah, they're quite attractive. So what's happening during that process is that your model of what a face should look like is winning the battle with what the vision system is saying. It's hitting your eyeballs and it's not matching face exactly, but the model of face is too strong. It's not until we start to line up. I think this should work. Somewhere around now, the sensory information is starting to get through and you're updating your model. And what you see is the consequence of a model plus the sensory data. So we can do things like this in experiments when we're thinking about pain. This is an experiment we did a long time ago, but it's one of my favourites. It's I would describe it as an elegant, simple experiment. We had supposedly normal volunteers. Now, we do experiments on people and we write the research article and we say, normal healthy volunteers participated in this experiment, but they're participating in a pain experiment. So what we should really write is unusual, questionably insane, impoverished people, probably students not doing very well on exams, volunteered for this experiment. But what we did is we put a very cold thermode on their hand. 10 times we did that. And every single time the thermode was minus 20 degrees Celsius. It's very cold. And we asked them a range of questions. But for 5 of the trials, we showed them a red light. We just showed them this red light as we were delivering the very cold stimulus. For the other 5, we showed them a blue light. Now, red and blue mean things. We have models of what red means, and we have models of what blue means. And then we asked these people a range of questions, but the critical question was, how much did that hurt? How painful was that? These are the responses. So every line represents an individual, and hopefully you can see 2 things. One is that on average, exactly the same thing at the hand hurts more if you see a red light than if you see a blue light. That's the first thing. Very consistent response, except for the occasional person. And I'm going to see if I can make the mouse thing do what it does here. Where is it? There we go, hang on. I can't do it. But if you look at the lowest score on the red side, it's a horizontal line. See that? And there's another couple of people who are horizontal. In neuroscience, we call these people idiots. Because they're not picking up on cues that will probably be helpful for their livelihood and safety. I always get asked, were they colourblind? I don't think they were. What about this situation? So the way that we produce visual experiences depends on a lot of things that we don't know we're considering. So just looking at these two panels, can you please raise your hand if the top panel looks darker than the bottom panel? So that should be all of you, really. But there's two ways we can do this experiment. I might just do the first way, where if you get your index finger and you align your index finger to just cover the middle part between those two panels. So you have to horizontally. If you can remove the middle part and then the bottom of the top panel and the top of the bottom panel, you should be able to see this happen. Let's go outside to do that. So that's what happens if we do it electronically. We're just removing information. So those two panels are actually exactly the same shade of grey, but when we put them into this environment, they look different because your brain has models of how sunlight works. This is clearly a situation where there will be sun in the sky and there is a shadow underneath. And your brain instantaneously combines your models with the data coming in through your eyes and shows you something that's not strictly true, but it's very helpful for negotiating the world. These are some of my favourite experiments done by an American group because of what they managed to publish in the papers. So this is looking at withdrawal reflexes. When you pull your hand away from a hot stove, you know, that sort of, wow, that's called a withdrawal reflex. And they did this in an experiment by stimulating with electrical stimulus, so electrodes on the foot, and they recorded the size of the muscle response in the leg, pulling the foot away. And that's what they were interested in. How big is the muscle response? And what you can see there in front of that participant is a little canister that will have odour in it, have some sort of smelly substance in it. In the first set of trials, they do it without any odour at all. That's called basal. They then do it with a pleasant odour, probably, I don't know, lavender, Ruth. Something pleasant, and there's no effect on the withdrawal reflex. Then they do it with a neutral odour, and there's no real effect on the withdrawal reflex. And then they use what they called fart spray. Published. So they put fart smell in the canister. What? The question down the front was, how did they get it in? That is terrific. I imagine it was synthetically. Maybe not. You probably see where we're going. What do you think might happen to the withdrawal reflex? So the foot withdrawal reflex is doubled in size. Now, aside from being funny, just think how remarkable this really is. That the models in the brain of what things mean are enough for this brain, in the presence of fart smell, to increase protection for your whole body. When I talk to doctors and physiotherapists about this, and I say, so what's the take-home message? They nearly always say, stop farting in the clinic. But the take-home message from a neuroscience perspective is everything matters. Everything matters when it comes to feelings. And when it comes to pain, a distressing, disabling feeling, everything matters. It matters what signs you have on the wall in your clinic. It matters how you look at people when they say, I've got a really sore back. In that moment, it matters how you look at them. It matters how you validate or not their experience. And it doesn't just matter that you have these indirect effects like, oh yeah, they know I care for them. The neuroscience tells us you have the potential to change the feeling because everything matters. I don't know what this slide's meant to be. Oh, okay. So this is an experiment that I thought of. How's this for a scenario? I thought of this experiment, gave the idea to the researcher. I was working in the same lab. And she said, oh, that's a great idea. And then I saw it published a few years later. This is a cool experiment. These people delivered laser stimuli, painful laser stimuli, to the bottom of the foot on supposedly normal, healthy volunteers. They randomly allocated one spot or the other to be described as this stimulus is probably safe, or this stimulus is safe. The difference? Probably. That's it. And then they asked, how much did that stimulus hurt? So at the sites where you've been told it's probably safe, it's more painful. Exactly the same stimuli. And what Katja also did is looked at where might this difference be mediated in the brain. So this is a brain scanning result from exactly the same experiment. This has clear implications for the way that healthcare professionals communicate to patients. If we send any data to their field of view that questions the safety of something, their brain will use that information when it's using the models. Practice makes models more powerful, and that's really obvious. I'm not going to tell you my story about that, but that's very intuitively sensible. It's exactly what Brenton has been talking about. The more we do anything, the better we get at doing it. The models of your body are important in what things feel like. So I'm going to finish with this little set of experiments because they were fun experiments to do. So this is an experiment called the rubber hand illusion. Now, I did this experiment with Meng. Meng's from Singapore. This is when I lived in the UK. And I just want to tell you a little bit about him because I really wanted to do this experiment on using prosthetic arms, realistic arms. And what you do in this experiment is that you put your real arm, his left hand here, behind a board so it's out of view, and then you put the fake arm in front of the board, and then if you touch both arms together while he's watching the fake arm, most people will get what's called a rubber hand illusion. And that is that they start to think the rubber hand is actually their hand. The brain is thinking you're messing with my models, and because vision is so powerful, I can see what I can feel, therefore that hand is mine. It's a very compelling illusion. But we wanted to use prosthetic arms, and I didn't have any prosthetic arms, so I went up to the John Radcliffe Hospital in Oxford, where I was working in Oxford, and I said to the prosthetics department, do you have any old prostheses lying around, like any fake arms or legs lying around? And he said, yes, we have 150 unclaimed arms. And I said, excellent, could I borrow a couple of them, please? And he went, I'll have to read the policy and procedures manual. And I said, this is why it is the formerly Great Britain. So I went away and I rang him 3 days later and I said, have you read the manual? He said, yes, I have. I said, excellent. Can I come and borrow a couple? And he said, there's nothing in there about members of the public borrowing unclaimed arms. So I said to Meng, and he's from Singapore where no one commits a crime. I said to Meng, let's go and steal some prosthetic arms. So we went up there and his job was to distract the prosthetics department. And I would go in the back door and take some limbs and run for it. So we did it. So Meng went up to the desk, and this is how he chose to distract everyone. He just went up to the desk and he just started going, and it really worked. everyone wanted to know why he was doing this, and they were saying, "What's wrong?" And he just kept going, looking over, and then he saw me sneak out of the other door with 3 arms and 2 legs, plus my normal arms and legs. And when he saw me, he did this. And we just imagine this, professor of brain science, followed by a small Chinese-looking man running down the main corridor of the hospital saying, "Taxi, taxi." So we got away with 3 arms and 2 legs, which I still have, which got me into trouble in Los Angeles airport, I might say. And this is the experiment that we did. We induced the rubber hand illusion. So it feels like the rubber hand is yours. And we are interested in what happens to your actual hand. And we looked at blood flow or temperature. And what these data show, there were 5 experiments that got to this result, that when we can induce the illusion, your hand temperature, the bottom trace, your real hand drops. Your other hand doesn't change. You let your foot on the same side, maybe that drops a little bit. But the real effect is at the disowned hand. I think this is a profound discovery because it tells us that what we think about our body changes physiological regulation of our body. And then we start thinking about disorders of body disownership, or body dysmorphia, or anorexia, phantom limb pain, where people simultaneously can feel like their arm is floating above their head and is heavy. These are feelings, and they are based on models plus sensory data. This is not just about blood flow. We did another experiment that showed that when we induce the illusion and then we put histamine onto the skin in a little pinprick, you get a bigger immune response, as though the brain is saying, "It's not mine and I don't want it." Now we can start thinking about, okay, this true two-way interaction between models, sensory data, what we feel, what our immune system is doing, what our cardiovascular system is doing, and from the fart experiment, what our movement system is doing. So a full circle back to my thoughts about the brain and body. I'm reminded by experiments like this that we are a unified organism. Our body is certainly influenced by what our brain is commanding. And you can see the devastating impacts of brain injury that Brenton's been talking about. Our brain is clearly influenced by our body. So much so that I would say we are a brain-body context organism. This creates a massive challenge for us when we're trying to solve problems of the body like pain, because we realise they're not problems of the body. But it also presents amazing opportunities because it says these are all the other windows that we might have to influence this system. And our research group's been pushing that way to try and look at, well, what other ways can we improve people's feelings in their body? Pain is the most obvious one. Stiffness is another one. Fatigue is another one. Thirst is another one. Hunger is another one. I need to wee is another one. They're all feelings that make us behave. And all of those feelings can become overdone so that you desperately feel like you need to wee when you don't have any urine in your bladder. So that you desperately want to eat when you don't have any problem with blood sugar. You desperately want to drink when your blood volume is fine. You desperately want to stop your foot from hitting the ground when your knee is actually safe. All of those feelings depend on sensory data. The biomedical model does that pretty well. And the models in your brain. And that's where I think the revolution is happening. I want to stop there. I have more slides, but I think that's the best place to stop because I said I'd stop 4 minutes ago. Sorry. Anyway, thank you. I'm sure we've got time for a couple of questions.
Time for a couple of questions, absolutely.
I don't think we've got any questions.
So what do I do about the chronic pain in my neck?
Yeah. Well, there's lots of things you can do. And if I could do a quick rundown of what we've learned asking people who have recovered from chronic pains, what are the most important things you learnt that helped your recovery? So we've done that. 350 people who have improved to some extent, in some occasions completely recovered from years and years of chronic pain. They tell us 4 things that they learnt that were really powerful. And I'll tell you where to go and find them, so don't write them down. All right? So the first one is that pain protects us and promotes healing. And that's actually really powerful because we now know that pain doesn't detect damage, it protects our body from damage. It's a really interesting mind mess. The second one is that persisting pain overprotects us and prevents full recovery. The third one is that there are always many factors that influence anyone's pain. And therein is the challenge and the hope, because the challenge now is to find them across every facet of your existence. And the fourth one is that there are many ways to retrain an overprotective pain system and gradually reduce its sensitivity over time and move towards recovery. And they're the 4 things that people who have recovered said they were the game changers when I really understood that. So if anyone had a question a bit like yours, if this is okay with you, say, so what do I do? My advice would be get curious. No pain, as in K-N-O-W, and no gain, K-N-O-W. No pain, you'll no gain. But learning about pain is really difficult to do. So if you can find a good coach, that would be great. Otherwise, go to painrevolution.org, and that's where you can start your journey. And there are fact sheets, there are little PowerPoint shows. I did have a slide up here about a book that's just available dedicated to osteoarthritic knee pain. If you're interested in that, go looking for osteoarthritic knee pain Mosley. You might find it. But I get royalties from that, so I've got a conflict of interest. And if you all bought that book, I could probably buy myself a coffee.
Thank you for a very interesting lecture. However, having had a husband who died of spinal cancer from the prostate, I'm just wondering, isn't there a limit to your message when it comes to that kind of very cruel chronic cancer?
Yeah, well, first, we know that particularly bone cancers and pancreatic cancers are extraordinarily brutal and painful. What we also know is that pain is the result of models plus sensory data, and one of the reasons that cancer is so problematic is that what's happening at your tissue level is so slow, it doesn't get detected by the detectors in our tissues soon enough. If it's very rapid, it gets detected more easily. So cancer can get around this pain system sometimes. What we also know is that understanding all of the contributors to pain applies to humanity. So there are projects in people with active cancer pain, palliative pain, pancreatic. We're involved in a study at UniSA looking at palliative pancreatic cancer patients. Rheumatoid arthritis with active flares. So I guess the opportunity of modern pain science is that it applies to pain. It's just that there's a lot of things that are relevant to pain about bodily protection. And there's an example where, of course, the system was screaming out to protect your husband and making his brain say, you got to do something here. And that's appropriate because he was in immense danger. So we do need to find, I guess we need to embrace the reality of the full complexity, which is everything matters, including what state your tissues are in and what's going on in the tissues of your body.
Thank you.
We have we can have a couple more questions if there are questions. Looks like no.
Can we just take a moment to appreciate how well these three people have successfully aged? Well done. I was slightly confused about successful ageing seminars, Ruth, because I was trying to work out what is failing at ageing. Like, if you're not successful at ageing, what happens? Like, I was not sure which way it would go, but.
Look, he's so provocative, isn't he, really? But there you go. I will ask Brenton to join Lorimer because I would like to give them a small gift. I'm not sure whether it's new data that might change the current model or whether it contributes to that, but nonetheless, I will show your appreciation and my appreciation by giving them a small bottle of something that might change their current body image, and hopefully, but seriously though, thank you both very much for what has been an outstanding seminar and has raised as many questions and want us to go and look beyond what you've said, which is exactly how it should be. Thank you so much indeed, both of you.